Okay, let's take a look at 4 different possible scenarios for a titration. Classic example of a strong acid with a strong base. But we could also have weak acids and weak bases come into play. Let's take a look at what the plot looks like and try to understand it. If it's a strong acid with a strong base, you got to be starting with a very low pH, since the only thing present initially is strong acid, and there it is, less than 1. It should be pretty close to a flat line as you drip in your strong base, because you still have excess strong acid, which is totally dissociated. Also notice that the product of this reaction is sodium chloride. That's simply a neutral salt, so it's not going to affect things at all. However, as soon as you get to exactly an equivalent of that stuff, you have no hydroxide present, nor do you have H plus present. It should be very close to 7. And as soon as you add one more drop of your strong base, then you've got pure OH minus in that solution, which is a strong base, and you get a nice rapid increase in pH, and then it will flatline out as the concentration of hydroxide is just added by 1 drop at a time. So it's a nice way to figure out the concentration of that known acid. If you're asking yourself what's the initial pH, well, it's got to be very low. How would we measure it? That's kind of a funny question, because we're doing the titration in order to find out its concentration. So we're going to have to get to the equivalence point. We could also say that since it's going to be a certain pH, and the negative log of that value will give you the H plus concentration. Until your titration's done, though, you can't really measure it. As titrant is added before the equivalence point, is a buffer solution created for this solution? That's a good question for a buffer chapter. And the answer is no, because we have a strong acid and a strong base. There's no weak acid conjugate base or reverse situation. But we could say that H plus is consumed to make your sodium chloride, making a neutral salt, so we have a slow increase in the pH. When you hit the equivalence point, it better be right at 7, since you're making a neutral salt. And afterwards, it should rise quickly because you have some pure OH minus in solution. All right, a weak acid with a strong base added. That's a classic example of a titration situation where you're going to make a buffer. In other words, we've got, say, a weak acid like acetic acid. We're going to drip in some sodium hydroxide of a no concentration, and we'll make some sodium acetate and water. Notice that we're not making a neutral salt. This is the conjugate base of this weak acid, which means that it is weakly basic, And so what will happen, as soon as you add it, you're making a weak base, so the pH won't stay flat. It will start to go up a little bit. Once you go through this range to the point where you're adding sodium hydroxide, you're making weak base a little bit more continuously, so the pH goes up a little bit. But once it's past a stoichiometric amount, then you have strong base present, pure hydroxide, right? And then it'll go way up. So the initial pH is not as low, since it's a weak acid, not a strong acid. And when you're going through this range, if you want to measure the pH, you would have to know the Ka values, since you have an equilibrium situation. This is classic buffer type problems, which we've learned how to solve. As you add the titration, you add the titrant, which means hydroxide. Is a buffer created? Yeah, because you're making the acetate in this case. And the buffer is created. You have a slow increase throughout this range. And then at the equivalence point, since you have a weak base present, you should be somewhere above 7. You're making a basic salt. Afterwards, it should go up nice and high, because you then have pure strong base that's sitting around in solution, which is completely dissociated, so it goes high at that point and flattens out just like it would up there. We'll talk in the next slide about the half equivalence point, which is a nice way to measure the Ka of a system. If you have a weak base with a strong acid, well, weak base you're starting with, so the pH will be high, but not that high, not up by 14. As you add the strong acid, that will react. Let's take a look. So we'll have weak base is ammonia. We add the strong acid, hydrochloric acid. This is an example of it. We have an ammonium system, so we have a weak base and its conjugate acid. Yeah, that's a buffer system type of situation. The initial pH will be relatively high, not crazy high, but relatively high. And as you add your acid, you will be forming the conjugate acid of that weak base, and therefore it'll go initially down because it's not a neutral salt, it's an acidic salt, and the pH goes down a little bit. And it drops somewhat as you're adding. Each time you add a drop, you add a little bit more of that weak acid, so it doesn't stay very flat. It's going to be continuously going down. But it's making an acid which has a very low dissociation constant, so it's not not much of that actual acid is in solution. That's why it's weak. However, once you go past a stoichiometric amount of HCl, then you have plain old H plus in solution that dissociates completely, and you get this giant drop. And at that point, you end up with just some adding a little bit more of H plus each time, and it flattens out, goes down in an equivalent way that one went up, because it's strong acid that each drop adds a little bit more, and it will increase slowly. So you are making a buffer system. You're making acidic salt. So at the equivalence point, it's got to be less than 7. And after the equivalence point, it drops down rapidly, and it's low. So be able to recognize characteristic titration patterns and be able to explain each part of the graph. And if you have a weak acid and weak base situation, well, these even don't normally show up in a chapter, but it does seem like the fourth combination. So let's simply point out that it's equivalent to the second or the third situation, but it's not going to be as drastic. And one of them will probably be in excess compared to the other at each part in the graph, so you can just analyze it for an individual case.